equals 82.3 e to negative 0.004 t. Excellent. What next? Of course, I have to clean it up. 79.1 over 82.3 equals e to negative 0.004 t. Very good. What next? I have no choice. Even if I want to do something else, I can't. So this is natural log 79.1 over 82.3 equals negative 0.004 t. How come I don't write natural log e? Because it's 1. So then I can determine t. T equals natural log 79.1 over 82.3 negative 0.004. So if you give me an approximation, I will put it in.
That's 82.3. I had 9.91, but I don't. 10, I had 9.9145.
Okay, so t is approximately 9.91, which means in the year 2020. Very good. Moving on to logistic growth model, the second application. Very good. Yes? Perfect. So here it is, problem 88. Caught my eye on page 538. 88 on 538. The function f of t equals 500,000 divided by 1 plus 2,499 times e to negative 0.92 t. Okay, models a number of people. Number of people. I have to take notes, measurement units and all. Number of people, f of t, in a city who have become ill with influenza t weeks after its initial outbreak. T weeks. In weeks. Part A. How many people became ill with the flu when the epidemic began? What do I have to do? Excellent. F of 0. Let's do this together. We can plug it in, of course, but let's do this together. So negative 0.92 times 0.
0.
Good. E to 0.
1.
Excellent. 1 times 2,499. 2,499 plus 1.
5.
200 people indeed. So initially, 200 people got the flu. Part B. How many people were ill by the end of the 6th week? F of 6. Let's plug it in. I would like to put it in y equals. Clear whatever you have in there. The top is only one number, so you don't need to put that in parentheses, 500,000. But now you divide and you have to put parentheses, 1 plus 2,499 e. Please put the power of e in parentheses, negative 0.92, and x, don't forget x. Close the parenthesis for the power, come down and close the parenthesis for the denominator. You must have parentheses around the denominator, must have parentheses around the power of e. What do we want to plug in again?
6.
Yes, second and table, and plug in 6. So how many people, we don't round up people, right? If you get 45,411.2, you're not going to say that you have 45,412. Even if you have 45,411.9, you cannot round it up. It's number of people. Yes. So how many people were sick by the end of the 6th week? Any questions? What is the limiting size of f of t, the population that becomes ill? That was one of the reasons why I wanted to put in the graphing calculator. So initially 200 people are sick. Then 6 weeks later, more than 45,000 people are sick. I want to see what happens 10 weeks later. I want to see what happens 100 weeks later. I want to see what happens 200 weeks later. I want to see what happens 300 weeks later. And I think we got the picture.
I used to put that in Y, like that, right? Because I
Yes,
had
yes,
it in there, but
yes, yes.
then I tried to delete and I deleted the whole thing.
So by week 100, everybody will be sick.
Yes. Which means, well, this is an assumption, right? We assume that there is no one visiting and no one leaving the city,
Okay.
right? That's an assumption. But definitely not, we assume that since nobody's visiting, the maximum number of people who get sick is the number of people in the city. I cannot, not more than that can get sick, according to the function. Okay? So I will say the limiting size of the population, C, as t approaches infinity, f of t approaches what?
5,000.
That's it. It cannot exceed the limiting size of the population. Questions? Yes.
Do I, because I'm trying to put it back in the right way, do I close the parentheses
Yes,
here?
but you have to have left parenthesis, right parenthesis, and you have x. So the left parenthesis before the negative sign, then the negative sign, then 0.92, then x, then close the parenthesis for the power, and then come down and close the parenthesis. No, with this one. We come down with this. Because you need to close the last parenthesis.
Okay. Oh, okay. But I
And
didn't
then-
but X is there.
It's fine. That's how the function looks like. And then you go to second and table, and now you punch in 0, and you punch in 6, and you punch in 100, and whatever else you want to see where it's going.
Okay.
Last type of function, the exponential decay. Any questions on this? Of course, the model will be given to you. You will not have to create anything here.
And this is which type of
Logistic. This is logistic. Okay, good. So the last one, the last application before chapter 5 is exponential decay. Okay, here's the formula for exponential decay. You don't have to memorize it. A of t equals a0 times e to negative kt. Do we notice anything? Very similar.
The negative.
Just the negative in front of k. The positive in front of k will make it increasing. The negative in front of k will make it decreasing. And we just saw a minute ago, look at this one. We just saw an exponential decay. We didn't even know it was possible for people, but it is. It's 0 e to negative k t. And we know that anything that has a negative in front will be a decreasing rate, will have a decreasing rate versus the one with positive. Very good. So let's choose the problem. On page page 539, problem 28. Let's read the problem. Use the exponential decay model, blah, blah, blah. We already have it. To solve the exercise, I'm taking notes. Half-life of iodine 131, that's not important, it's a radioactive substance, is 7.2 days. How long will it take for a sample of this substance to decay to 30% of its original amount? Okay, so let's look at the model and decide what we don't have. And the answer is we don't have a lot, right? We do not have the original amount, which is A0. We don't know how much iodine we have. We do not have the decay rate, which is K. Like before with the previous problem with the exponential growth model, we did not have the original, we did not have K. Here we don't have the original, we don't have K. However, the information given in this problem is a little bit more ambiguous. In the previous problem with the exponential growth, we were given 2 points. Nice. With 2 points, we were able to determine A0 and K. But here, I'm not really given points. I'm only told that half-life is 7.2 days. Let's make up a point out of it. Let's think. Always remember, time is independent. Time must be on the x-axis. Time must be the first coordinate of the point. Always. If time is involved, time is always the first. So we're talking about half-life of 7.2 days. So what is the point then? Of course. Good. So now, what is this? What did we say about half-life? We have 100 milligrams of whatever. In 7.2 days, we'll have 50. In 7.2 days more, we'll have 25. And more, 7.2 will have 12.5, and so on and so forth. But now, in this case, I do not know what I have. I have A0. In 7.2 days, I would have
A0 times 0 times 8.
half of A0. Exactly. And that's what it is. That's exactly the point pertaining to half-life. Is that clear? I don't know I don't care what I have, but I know I have A0. And the point must be that 7.2 days later, what I will end up having is A0 over 2. Today, I have at point 0, comma A0, 0 time, comma A0. But 7.2 days later, I have 7.2, comma A0 over 2. So you could say that the first point is this. The next point must be this. So at time 0, I have A0. But when time is 7.2, I have half of A0. I want to plug this point in the function. So tell me how to plug this point in the function.
7 point.
Careful. What is this? What is this? I'm plugging this point in here. What is this?
That's the time.
That cannot be the time. This is the amount. Exactly. A0 over 2 equals A0 times E to negative K times? Excellent. 7.2 indeed. Do we understand this? This is crucial because I don't want you to memorize. I can tell you, memorize that the half-life is natural log 2 over r. But why? Is it clear? Yes. When time is 7.2, the value of the function is a0 over 2. When time is 0, the value of the function is a0. Okay, let's look at this equation. And let's clean it up. And then I will ask you, what are we solving for? K, that's what we need. So how do I clean this up? Can I simplify both sides by anything? By a0, indeed. Indeed. So 0.5 equals e to negative 7.2k. I divided a0, 0.5 times a0 by a0, and I divided a0 from the other side. So I divided both sides by a0.
Negative 5.5.
Because a0 over 2 is 0.5 times a0. It's the same thing. Or 1/2
So 1/2, okay.
times a0. These are all the same.
All right, okay.
Okay, it's completely cleaned up. And now what? What can I do? I'm solving for k. K is my unknown. I have to. There is no other way. So natural log 0.5 equals negative 7.2k. And then tell me how I get k. It must be natural log 0.5 over negative 7.2. So let's find k with the calculator. Please plug in natural log 0.5 divided by, in parentheses, careful, negative 7.2. And when you start with a negative sign, you have to use the negative. Not it was 2. I'm sorry. Thank you. Very good. So the radioactive decay rate is 0.0963. Normally 4 digits are required. Okay, so now I have the model. I put that back in the model. Let's put it back in the model. A of t equals a0 e to negative 0.0963 t. Only now I can answer the question. Let's read the problem one more time. So all this work was, I took the half-life, I created a point, I plugged in the point to find k. I took the half-life, and I said 7.2 comma the original amount over 2. And I plugged in that point to find the k, the radioactive decay rate. Now, let's read the problem one more time. The half-life of iodine 131 is 7.2 days. How long will it take for a sample of this substance? How long it will take for a sample of this substance to decay to 30% of the original amount? How long it takes for the amount to be 30% of A0? How do I write that? 30% of A0. What operation do I use? Multiplication. Very good. 0.3 A0. Excellent. Now I want to plug this point in. So please tell me what to write. Of course, T is T because I don't have it. This is what I'm after. I can do that. So what will you write? Let's start with the left-hand side. Exactly, 0.3A0. Awesome. The right-hand side is A0 e to negative 0.0963t. And what do you think I'm going to do first? Of course, I'm going to get rid of something I don't have. And I can get rid of. Yes, I'm dividing both sides by A0. I get 0.3 equals e to negative 0.0963t. And obviously, my only chance is natural log. Let's get t. Before we continue, let's think for a moment. From 100% A0 to 50% A0, how long it took? 7 point. But from 100% to 30%, do you expect less than 7 days or more than 7 days? Of course more. It took 7 days to get in half. But I want it much lower to 30%, so it has to be more than 7 days. Very good. So natural log. So natural log 0.3 equals negative 0.0963t. So then t must be natural log 0.3 negative 0.0963. And what did we get? 12.5 days. Expected, right? If I take 7.2 days to get from 100% to 50%, from 100% to 30%, it must take longer than 7 days. Does it make sense? Okay, this is the end of chapter 4. Now let's think of, we still have 10 minutes, so I would like to practice whatever you want me to look at, or whatever you want us to look at. Of the radioactive?
Yeah.
Okay, very good. Any preference? Is radioactive okay?
I feel like when I'm doing this on my own, like I'm not gonna come up with like A0, like A
Okay.
over 2.
Very good. Let's do that. Would you like to choose?
For page, was it 5?
Page 529,
Or 539?
529, 530. So, for example, 28, 30. Oh, half-life of aspirin. Interesting. Yeah. Okay, 30. Excellent. We need to know. So CE applications not only for radioactive decay, but also for medicine. Yep, yep. So the half-life of aspirin in your bloodstream is 12 hours. Half-life, 12 hours. How long will it take for the aspirin to decay to 70% of the original dosage? So if I take an aspirin right now, it's completely out of, it's half of, in my bloodstream, I still have half of it 12 hours later. The model is not written in this problem, but you will get the model from me. So this is definitely A of t equals A0 times e to negative kt. You don't have to memorize this. I don't have the original amount, but I know that if I take a pill right now, aspirin, 12 hours later, in my bloodstream, I still have half of what I took. That is sufficient for us to come up with a point. 12, comma?
A0 over 2.
Excellent. So I took A0 right now. AO is fine too. A sub O, A sub 0, same thing. So I took A0 right now, and 12 hours later, this is the point. 12 hours later, I still have in my system A0 over 2. I need this point put in the function, in the model. And I'm waiting for you to tell me what to write. We start with the left-hand side. Or if it's easier, you can write it as 0.5 or 50% of A0 equals, yes, times e to negative k times, exactly. So that's how we put in the point. When times 12, the amount is 0.5 times A0. Perfect. What happens next?
Get rid of it.
Yes, because I don't even know how much I took. So then 0.5 equal, and I don't care. So I'm doing all this for what? What am I trying to find? Indeed. How do I find k? What do I have to do? Yes. Apply natural log. So natural log 0.5 equals negative 12k. Therefore, k equals natural log 0.5 over negative 12. And when you have it, give it to me. How much? 0.05. 78. Perfect. So now we have the model. A of t equals A0 e to negative 0.0578 t. Excellent. And now we can answer the question.
I'm sorry. I'm not putting it in the wrong spot again. What is the wrong screen?
No. So here we are doing this. So
Oh, without not putting
yeah,
it
because
in.
we're not putting x. When we put x, we go into natural. Yeah. So we have natural log of 0.5 divided in parentheses. This must be parentheses. And the little negative sign. Can anyone else confirm the 0.0578?
So,
I trust Ella, but I just want one more
Yeah.
confirmation. Yes?
yeah, I got the same.
Perfect. So this is the model now. We are ready to answer the question. How long till we have not 50% of A0, but 70% of A0? Can anyone create the point?
How long?
How long till we have 70%?
So,
Hold on, let's read it one more time. It decays to 70% or 70% is decayed. So careful, careful, I shut my book. To decay to 70% of the original. Okay,
So it's decayed 30%.
exactly. But I have to write the amount that is in my system, not how much went away, right? So the model is what I have now from what I took, not what dissipated. This is what I have now at this present moment in time, and I took this. So what is the y value? 0.7 A0. And time is unknown. So please put this point in the model. The left-hand side. Very good. Equals A0 e to negative 0.578 times, I don't know. This is what I'm looking for. Okay, how do I clean it up? Yeah, I don't even need it. I don't even have it, and I don't need it. 0.7 equals e to negative 0.0578 t. What happens next? Exactly. So natural log 0.7 equals negative 0.0578 t, and I should write times natural log e. Why not? Because it's 1. Yeah, I should write times natural log e, but I don't because this is 1. Very good. So then t equals natural log 0.7 negative 0.0578. Now, we know that it takes 12 hours to get to 50%. From 100% to 50%, 12 hours. From 100% to 70%, more or less than 12 hours? Of course, right? If I need 12 hours to get from 100% to 50%, only reduced by 30%, it should be less than 12 hours. Okay, that's like a checkpoint. So what did we get? How many hours? Is it 6? 6.17 hours. Very good.